Today I will be presenting Trace Compass and how we can better understand the distributed application at different layers, from the network layer up to the application level. So first of all, what is Trace Compass? For those who've been here before or who have used it, it's formerly known as the TMF, or the Linux Tools LTTNG Eclipse plugin. It's mostly maintained by a team at Ericsson and also helped by a research team at Polytechnique, but there's also contributors worldwide. First, it's a trace visualization tool to visualize, to see different analysis on a trace. It's distributed either as a standalone rich client application, and it's also available as Eclipse plugins through Linux tools. And it's also an extendable framework, so we can add support for new trace types, we can build new trace analysis, and now recently with data-driven analysis, it's easier than ever to do that without even needing to write any source code in Java. So, Trace Compass, TMF, why did we make the change? Well, first of all, if we go back in history, Linux tools is a set of Eclipse plugins to interact and work with Linux tools directly from Eclipse. Since we started as support for LTTNG, that was the logical place to be. But as the years came, we started supporting more and more trace type, and we went much beyond Linux only. So it was also the logical evolution to become our own project, and also, well, Trace Compass sounds a lot sexier than TMF for branding. So what trace types do we support? Of course, first we still have LTTNG and any CTF traces, LTTNG UST and LTTNG kernel tracers. We also have custom text and XML traces so that we can take any log file that has a predefined format and support it. BTF traces, that's the Bosch trace, better trace format from Bosch. That was a request from a client. We also have GDB traces for debug. Recently added the Pcap traces, so we can analyze TCP dump output. And also, as a prototype, we even can support Windows traces, but that needs conversion to CTF that was provided by a team at Google. And what analysis do we support built-in? For LTTNG kernel traces, we have the control flow view, which shows the state of different processes at different time of the trace. The resource view, which shows the usage of resources through time in the trace. So CPU, IRQs, soft IRQs. CPU usage shows the usage in percentage of CPU of the different thread. For LTTNG UST, we have a few built-in analyses, like the memory analysis for traces taken by preloading liblttng libc wrapper. We have a call stack view that showed the call stack of any application that was compiled with the F instrument function. For Pcap traces, we can show the network stream list. That's every stream between two endpoints in a different protocol. And we also have meta-analysis that can apply to any trace type for data-driven analysis, network trace synchronization, virtual machine analysis, and critical path analysis. In bold are those I will show today. So let's go to the demo. I will be demonstrating a few features. I hope it all works fine. I will have one distributed application with 3 use cases. So I will run them first locally, then on 2 machines on the network, and on 2 virtual machines. First, just a presentation of the application that will be demoed. I traced an MPI application that has 6 threads, 1 server thread that sends an imbalanced workload to the workers and then wait for all workers to be finished their work. The worker, there's 5 worker threads who receive a workload from the server, does the work, and then wait for everybody to be finished. When everybody's done, we start another cycle, and we have 8 cycles in the application. So the first use case I run was to run locally, only on one machine. So what we have from the built-in analysis, with each experiment I did, I have kernel traces and UST traces. So with what is already built in, we can see the control flow view here, where yellow means the process is blocked, green and blue means the process is running in user mode or syscall, and orange is the process waiting for CPU. So what we see here, it doesn't tell me much as an application developer. I see a lot of imbalance processes. Those are the MPI processes. So from that, I can guess that the processes that are green running are probably my worker and server threads. If I was the OpenMPI developer, probably this would tell me a bit more, but as an application developer, this is not very helpful. I don't see the 8 cycles I programmed. So what can I do? Of course, the developers of Trace Compass didn't put my application in the software. So I will have to do it myself. How? Well, if we go back to the state of our application, whoops. I put UST trace point to mark where for each state transition. So if we look at the worker start work trace point will pass from the worker idle to the worker at work state. Worker wait will go to will tell us that we go to the worker wait state, and worker wait means we go back to idle and wait for the next workload. So how can I model that? We'll take one transition, the one from idle to at work. We need to have an idea of how we want to model that in the application. So we want to show the state of the application for each worker. So we have what we call an attribute that would be worker, the ID of the worker. Each event will have a field, which is the worker ID. So worker/worker ID will become worker at work when we see that trace point. So we can define that in XML. So first we define what we call a state provider. That's our model of the application. We define our states. So worker at work has a value of 2 for no apparent reason. And we define event handler. That's what we do when we receive that event. So here we handle event MPI imbalance worker start work. And we will change a state. We'll change the state of worker / we use the event field worker ID, and that becomes the value of worker at work. So we do that for every transition we have in our system, and with that we will get a history of the state of every attribute, so every worker, and we also have one for the server. What do we do with that? We can visualize it. Add the graph. What's supported so far are time graph views. That's a view like the control flow view with the bars and the entries on the left. And XY views, which are just XY charts. So here, we simply define that we want to do a time graph view. We define the values that we have. We give them each a color to identify them. And we show what we want to have for entries. So we want all workers. Worker/star would mean all workers. We display the attribute itself. That would be the state, like we defined in the previous model. So with that, the full XML file, I have it here somewhere. The full XML file looks like this. A lot of copy-paste. It's about 100 lines of XML code. We need to import that in Trace Compass with import XML analysis. Now it's already imported, so we'll just see the view. And here we have a much more interesting model of our application. We clearly see the 8 cycles, where it starts, where it stops, the clear barrier. So that's much more helpful for an application developer than just the control flow view built in TMS. So now, the second experiment I did was to run this application on 2 machines on the network. First, let's see, I ran them and oops, my 2 machines were not with the same clock. So here on one side, I can zoom in and I see something. And on the other side of the view, something else. That's not very helpful. But I traced also the TCP exchange between those 2 machines. And with TCP packets, we can match a few fields. And once we match 2 events, we know that this event that was sent from one machine was received there. We have a synchronization algorithm that takes those event match and calculates a best formula to bring both trace time to the same reference time. So like we can do here, just synchronize traces. You see traces are being synchronized, the number of matches immense. So we will cancel it. So now, cancel. Okay. I will open the one that's already synchronized. Close the others. And so now I have a much better view of my application. Both my traces are now at the same time reference. I see again the clear barrier between the cycles of the application, so that's all good. So now I will introduce a new trace type that has been added recently, the Pcap trace. What we see here in the event list is the dump of the Pcap trace. Every event, the source IP, source port, the protocol, the content of each event. With that, I can see a list of streams for every protocol. Like here, from one endpoint to another, the Ethernet, I have the MAC address of all the possible endpoints. IPv4, I see every pair of IPs that has communicated during that trace, the number of packets, bytes exchange, packets in one direction, in the other direction, start, stop, TCP transmission, UDP. And for each of those, if I want to see only the packets from one of those streams, I can right-click on it, extract as filter. So now I have a new filter. Here I apply this filter and I will see only the exchange, the packet exchange between my 2 machines. Wrong filter maybe. Ah, this is the right one. So if I go back to my trace, to my experiment with all the traces, I see with the TCP dump trace, the events of the TCP dump are put in there. So I can right click, I made a filter that filters the events both from the TTNG kernel trace that correspond to the TCP packets and the TCP output. So if I go down, here I see one exchange, I can follow it. This is the output from one machine. We see it has the same sequence number, act sequence, and it's received right after. So the TCP dump comes right in between. So we can follow, we can see what happened on the network of our trace. Last experiment I did was to run it on 2 virtual machines. So here I have first experiment. I synchronize the traces beforehand. If I go back to my thread view, I still have my thread view here, but the barriers are less clear. Like in the other experiments, I could really see now it stops, all the workloads are sent, and we start another cycle. But here, they don't all start at the same time, and we even see purple state that we didn't get to see in the other traces, because at this zoom level, it was too low. Okay, so now it refuses to answer. Okay, so let's go to the backup plan, screenshots. And if I was to zoom in on the MPI processes, I would see that there's a few system calls that are much longer than they should be. Like, we could see that there is like 13 milliseconds for a get time of day. That looks suspicious. So how can we debug that, knowing that it's coming from two virtual machines? We'll see first, we'll correlate it with the trace from the host itself. So what we see is a bunch of QEMU processes here. Do this. And the QEMU processes are being preempted all the time. So we have this zebra-like representation of those processes. And if we were to look at the resource view, we would see that at any given time, there's only 4 QEMU processes on the CPU at a time. So that means that's the way I configure my virtual machines, that even though each virtual machine has 3 virtual CPUs, they actually fight for the resources of only 4 physical CPUs. So that's why they preempt each other all the time. Let's go back and see if the demo is back. Okay. So what can we do with that? Because we saw in the traces from the virtual machines only, we didn't see all those preemptions. So we have a virtual machine view, which shows us the state of each virtual CPU. And this looks pretty much like the view of the QEMU processes. The virtual CPU view mirrors what we see in the QEMU process view. And if we expand one of the virtual CPU, we see the different processes from the guests that have been running on that CPU. And if we go down to our MPI process, we have a much more accurate view of the control flow view this way. Well, again, let's go back to the screenshots. So we see here that instead of seeing that the process is running all the time, we see it as running, but we have the information that it's preempted. So even though the virtual machine thinks it's running, it's actually not running. And what can we do with this information? We have a virtual machine preemption view that will show what is actually running instead of the process that we think is running. So like here we see the MPI imbalance process. There's a hole there, it's not running. What is running instead? It's another MPI balance from another virtual machine. And it's often, unsurprisingly, preempted by another MPI process from another machine, but sometimes it's also preempted by something from the machine itself, like the LTTNG consumer D sometimes take the place of the MPI process. And if we could scroll down lower, we would see that there's also processes from the host that are running instead of this virtual process. So that concludes the demonstration. So what future work do we have on Trace Compass? On the research side, the data-driven analysis is receiving a lot of love these days. We want to be able to define visually what I did earlier with the XML file. We want to be able to use the state diagram and generate automatically the XML analysis. We want smart filters and be able to do user-defined action on those filters. For now, the filters, you have to define like an event with one given field, but now we want to define like a series of events, like this event with this field followed by this event and this other field. If it takes more than this time, for example, we will display a view, or we will do something else, anything. And also we want to show statistics, more statistics, any statistics, have higher level events from a series of events. So much more on the data-driven analysis. Also GPU traces and analysis are being done. We also want to be able to compare traces from different execution, like what is the difference between this trace and this trace? Why is this trace using more memory than this other one for no reason apparent? And also from the Ericsson team, they are working on the live tracing with Trace Compass. So we can control live tracing from Eclipse. And also there's work to improve performances with large experiments. So that's it. Here's a few resources on the presentation today and also generally for Trace Compass. Any questions, comments, requests?
Hi, could you please elaborate a little bit on how you do the trace correlation between the data sets? Is that also data-driven? How you do the correlation? You had trace from those two different machines.
Yeah.
So is that correlation that you have done, is that also data-driven or not?
Not yet. It's not yet data-driven. The correlation, the traces from the network is really just TCP packets that correlate them, but that would be an easy low-hanging fruit for adding data-driven analysis to be able to do that data-drivenly. So if you know, for instance, you have a two UST trace and you have yourself events that can match from two, then it will be easy to add. Well, right now it's not that hard. It's just adding one small class to TMF. But if it's data-driven analysis, if it's data-driven, it will be much better. Are you talking about the virtual machines as well, or?
Yes, yeah. Also about the virtual machine.
Yeah, the virtual machine is a bit trickier. Like the question I was asking this morning to that gentleman on the QEMU. We need to have the KVM trace points on the host trace that needs compiling LTTNG with the full source tree, and we also have custom kernel modules that we need to insert both in the guest, so that the guest needs to be Linux, of course, and on the host that do an hypercall, and that hypercall triggers a trace point on the host, and there's an event field there that allows to match the two events. But in this example, the correlation between the two machines, the three machines, have been done also through TCP packets.
Other questions? Okay, thank you, Geneviève.